So we turn now to completing our analysis of the relationship between the change in internal energy, delta U, the change in enthalpy, delta H, the work and the heat, by filling this matrix out that defines the change in entropy along each one of these trajectories. Because when we've done this, we have the complete thermodynamic analysis of the system. So let's move forward and calculate delta S for each of these trajectories. So let's take the isobaric case first. Isobaric means that the pressure is constant, which means that delta P is equal to 0. And we're going to designate this as pathway A. Now, along the isobaric path, we calculate delta S using our macroscopic formulation as delta Q divided by the temperature along that pathway. But we know how to calculate the integral of dq over t because we've developed a great deal of experience in calculating the heat along each one of these legs in a Carnot cycle. And so we know that the heat added along a constant pressure surface is equal to the number of moles times the molar specific heat capacity times the change in temperature, and we have to divide through by the temperature, and that gives us the quantity, the number of moles times the molar specific heat capacity at constant pressure times the logarithm of the final temperature divided by the initial temperature, because we went from T initial to T final in our integral. Now we move on to the isochoric case. The isochoric case is a situation in which the change in volume is equal to 0. That means we're following this pathway, which we'll designate as pathway B. So the volume remains fixed during the course of this trajectory. Okay, but we can immediately calculate delta S because we know that that's the integral along that pathway of dq over t. It always is. We can define that immediately. So now we have the integral of dq, but now that's the number of moles times the molar specific heat at constant volume times the change in temperature, and then we have to divide through by T. So this is from T initial to T final. And so that gives us the number of moles times the molar specific heat at constant volume times the logarithm of T final over T initial. So let's look at the isothermal pathway. Isothermal means constant temperature. That means that delta T is equal to 0. And that means that we're going to be following pathway C, which is the isotherm. And the isothermal pathway with delta T equals 0 means that delta U is equal to 0, but delta U is equal to Q plus W. So Q is equal to minus W. So when we calculate the change in entropy, that's going to be equal, as it always is, to dq along that reversible pathway divided by the temperature. So if I'm going to express this now not as dq but as dw, then I have to reverse the sign. So I have a minus the integral of dw over t. But I know what dw is. We've worked that out many times before, so now I have minus the integral of minus p dv, and I have my temperature still in the denominator. Well, now I use the perfect gas law. PV equals nRT, but that means that when I look inside the integral, I have P over T. So if I divide through by T, that gives me nR over V. So I can substitute that in directly, and I can also eliminate those negative signs. And so P over T is equal to N R over V. And now I have a dV from my initial volume to my final volume, and lo and behold, that's equal to N R log, natural log of the final volume divided by the initial volume. So that leaves me only one more pathway to deal with. But the nice thing about the last pathway is it's the easiest because it's adiabatic, and I know any adiabatic pathway is defined by the fact that Q is equal to 0. There's no exchange of heat between the system and the surroundings. So that means that dQ is also equal to 0, and that means when I write my expression for calculating delta S from this macroscopic point of view, I have dQ over T, and that's identically equal to 0. But now we're ready because we worked so hard in calculating delta U, delta H, work and heat over those 4 different pathways. We only have to put in our calculation of delta S, and we have the complete thermodynamic matrix, which turns out to be the most powerful way of analyzing thermodynamic problems. So we can simply put in what we've calculated. Along the isobaric pathway, where pressure was fixed, that's equal to nc sub p times the logarithm of the final temperature divided by the initial temperature. The entropy change along the surface of constant volume is exactly the same functional form, but now I have the molar specific heat at constant volume, C sub V, but again times log of T final over T initial. When I calculate it along the isothermal path, or delta T is equal to 0, I had N R log V final over V initial from my previous calculation, and then I have a nice big 0 for delta S along the adiabatic pathway.